Growth and decay. As for the growth, it happens when the amount increases over time. The larger the quantity, the faster it grows. And for the decay, it happens when the amount decreases over time. The larger the quantity, the faster it decreases. To sum up, growth and decay describe how a quantity changes over a time, where the rate of change depends on the current amount. Have you ever wondered how living organisms grow and decline over time? Scientists use mathematical growth and decay models to better understand these patterns and to explain how population increase, slow down, and eventually decline. Microorganisms such as yeast provide a simple yet effective example for observing this process, as their growth and decline can be measured and analyzed over a short period of time. In this assignment, mathematical concepts are applied to study yeast growth and decay under controlled conditions. By analyzing changes in yeast population over time, the relationship between mathematics and biological can be clearly demonstrated.
Guys, the yeast is rising. Even after 1 hour of waiting, how are we going to make a bread dough?
It's okay, we can try to make another one. We have 8 grams of yeast, 4 grams of sugar, and 110 grams of warm water. My mom said, in 3 hours duration, the yeast supposed to rising until 32 grams.
Then, let's do another one and wait for 1 hour. And how much is time it takes to achieve 20 grams of yeast?
One hour later.
Wow, the yeast is show an improvement. How much do you guys think the yeast grows?
During our bread making experiment, 8 grams of yeast were used and expected to grow to 32 grams after 3 hours, and wanted to know how much it would have grown after 1 hour. We also wanted to find out how long it would take for the yeast to reach 20 grams under the same conditions.
Let's do a calculation to know the growth of the yeast.
This calculation is based on the exponential growth of yeast. Initially, the amount of yeast is 8 grams mixed with 4 grams of sugar and 110 grams of warm water. Since yeast grows continuously over time, its growth can be modeled using the differential equation dy over dt equal to ky, where y is the amount of yeast at time t and k is the growth constant. The general solution of this differential equation is y equal to c exponential power of kt. To find the constant c, we use the initial condition y equal to 8, substituting t equal to 0, give 8 equal to c exponential power of 0, so c equal to 8. Therefore, the yeast growth model becomes y equal to 8 exponential power of kt. Next, we are given that after 3 hours, the amount of yeast is 32 grams. Substituting t equal to 3 and y equal to 32 into the equation gives 32 equal to 8 exponential power of 3k. Dividing both sides by 8, we get 4 equal to exponential power of 3k. Taking the natural logarithm, ln 4 equal to 3k. So, we get k equal to 0.4621. Thus, the final growth model is y equal to 8 exponential power of 0.4621t. Using this model, we can estimate the amount of yeast after 1 hour. Substituting t equal to 1, y equal to 8 exponential power of 0.4621, which give approximately 12.7 grams of yeast. To find the time second for the yeast to reach 20 grams, we let y equal to 20. So 20 equal to 8 exponential power of 0.4621t. dividing by 8 give 2.5 equal to exponential power of 0.4621t. Taking the natural logarithm, ln 2.5 equal to 0.4621t. Solving for t equal to ln 2.5 over 0.4621 equal to 1.98 hours. Therefore, it takes approximately 2 hours for the yeast to grow to 20 grams.
It's raining. We should grab our laundry. Let's go.
The next day.
We forgot to take the yeast at pantry yesterday.
Let's grab our yeast at pantry.
Let's go.
Ew, it looks like our yeast has decreased and gone bad.
I'm curious to know how much the yeast decayed.
When the yeast was left overnight, we wondered how much would have decayed after 24 hours by applying mathematical growth and decay models.
Let's do a calculation. Let's go.
Because the yeast is decreasing, we use the decay formula to find how much the yeast decreased after 24 hours. The situation is represented by the differential equation dP over dt equals to Kp. Next, we separate the variables so that all terms involving yeast are on the one side and time is on the other side. After that, we integrate both sides of the equation. From the integration, we obtain a general exponential formula. P equal to C multiplied with exponential power of Kt. Optimum amount is increased in 32. So for the decay, we use 32 grams as initial amount of the yeast. Substituting C equal to 32 into the equation, then the decay model will become P of T equal to 32 times exponential power of Kt. Next calculation, we want to find the amount of yeast after 24 hours. To do this, we substitute the value of time, which is 24, into the decay formula. We substitute the decay constant, which is K equal to negative 0.4621 into the model. This gives the formula P of T equal to 32 multiplied with exponential to the power of negative 0.4621 times T. The negative sign shows that the yeast is decreasing over the time. We find the amount after 24 hours by replacing T with 24. This gives P of 24 equals to 32 multiplied with exponential to the power of negative 0.4621 times 24, which simplifies to 32 multiples exponential to the power of negative 11.0904. Using a calculator, we get a final value which is approximately 0.00049 grams. In conclusion, the yeast undergoes exponential decay. Starting for 32 grams, the amount decreases rapidly, and after one day, only 0.00049 grams of yeast is left.
Now we already know the amount, the timing using the yeast. From here on, we can learn from our mistake.
Then, what happened to the bread dough that we want to make?
Oh, bad. Maybe we should try next time. In conclusion, we learned that first-order differential equations are used in real-life situations like in solving growth and decay problems. Example of growth can be seen in human population increase and plant growth, while decay occurs in food spoilage and the decrease of a battery power over time. This assignment shows how mathematics help us understand the growth and decay of living organisms. By using growth and decay models, we were able to study how yeast grow from 8 grams to an assumed maximum of 32 grams and how it grows slow over time. This reflects what happened in real life, where organisms cannot grow forever due to limited resources. The mathematical models also allow us to estimate the yeast mass after 1 hour, find the time needed to reach 20 grams, and predict how much the yeast would decay after 24 hours. Overall, this experiment clearly shows the connections between mathematics and biology and how growth and decay models can be used to explain real-world biological changes in a simple and practical way.